So good evening one and all. We are going to discuss about the problem of estimating power spectral density of a Whitson stationary random process. Power spectrum is actually obtained from the Fourier transform of autocorrelation sequence. Therefore, estimating the power spectrum is equivalent to estimating the autocorrelation. For an autocorrelation ergodic process, we know that it is obtained from this formula. It is called autocorrelation ergodic time average autocorrelation formula. If x of n is known for all values of n, estimating the power spectrum is a straightforward problem. So what you should do, you have to determine the autocorrelation sequence and then you have to compute Fourier transform. So what are all the difficulties in this approach? Because still spectrum estimation is found to be a challenging problem. The amount of data that one has to work with is never unlimited, and in many cases it may be very small. Such a limitation may be an inherent characteristics of a data collection process in quite a few examples, such as the analysis of seismic data from earthquake, in which the signal persists only for a short period of time. It is also possible that a limited data set is imposed by the requirement that the spectral characteristics of the process remain constant over the duration of the data record. For example, in speech processing applications, a stationarity requirement will restrict the length of time over which the signal may be assumed to be approximately stationary, probably for a few milliseconds or less than that. The second difficulty is that the data is often corrupted by noise, contaminated by an interfering signal. So spectrum estimation is a problem that involves estimating px of e power j omega from a finite number of noisy measurements. In some applications, spectrum estimation is done using a priori knowledge about the process, how the process is generated. For example, if I know x of n, that it is an autoregressive process, that it consists of one or more sinusoids in noise, this type of information may then allow a person to parametrically estimate the power spectrum, parametric power spectral density estimation. Sometimes to extrapolate the data, sometimes it's autocorrelation in order to improve the performance of spectrum estimation algorithm. So there comes a question, what are all the applications of spectrum estimation techniques? For example, in the case of Wiener filter, smoothing filter, before it is to be designed and implemented, the frequency response of a non-causal Wiener filter will be given by h of e power j omega, which is equal to PD of e power j omega divided by power spectrum of d of n, PD of e power j omega, and power spectrum of the white noise. So power spectrum of the d of n, power desired output of the Wiener filter, power spectrum of the noise v of n must be known to work with non-causal Wiener smoothing filter. Therefore, before a Wiener smoothing filter operation is designed and implemented, the power spectrum of both d of n and v of n must be determined. So these power spectral densities are not generally known a priori. They are not available a priori. We need to estimate from measurements. Another application with the problem of estimating measurements. For example, it plays an important role in signal detection and tracking. A sonar array is placed on the ocean floor to listen to the narrowband acoustic signals that are generated by the rotating machinery or propellers of a ship, whether any ship arrives or not. Once a narrowband signal is detected, the problem of interest will be to estimate its center frequency in order to determine the ship's direction as well as velocity. Complete sonar array operation is implemented, shown narrow band signals that are typically recorded is in a very noisy environment. on the ocean floor. Signal detection, frequency estimation are non-trivial problems that require robust, high-resolution spectrum estimation techniques. Would you agree with me or not? So, signal detection and frequency estimation in a noisy environment, such as in case of sonar array which is on the ocean floor to know about the narrowband signal and estimation of center frequency, is a non-trivial problem that require robust, high-resolution spectrum estimation techniques. Some more examples can be given like this: harmonic analysis, harmonic prediction, time series extrapolation, time series interpolation, spectral smoothing, bandwidth compression, beam forming, hybrid beam forming, direction finding of arrival of incoming signals, what not. N number of applications are available. Normally, there are two approaches for spectrum estimation. First includes classical and non-parametric method that begin by estimating the autocorrelation sequence from a given set of data. Power spectrum is then estimated by Fourier transforming the estimated autocorrelation. It is called non-parametric approach. Whereas the second class of spectrum estimation, it is called non-classical parametric approaches, which are based on using a model in the process in order to estimate the power spectrum. If it is known that X of n is a pth order autoregressive process, then the measured values of X of n may be used to estimate the parameters of the all-pole model, AP of k, and then the estimated model parameters AP of k cap may then be used to estimate power spectrum as given in the equation. So, let's see the non-parametric models in general, non-parametric techniques of spectrum estimation. These methods are based on the idea of estimating the autocorrelation sequences of a random process from a set of measured data, X of n, observed data, and then taking to the Fourier transform to obtain an estimate of the power spectrum. Periodogram, a non-parametric method, was actually introduced in the year of 1898 by Custer in the study of periodicities in sunspot numbers. The periodogram is very easy to compute, but it is limited in its ability to produce an accurate estimate of power spectrum. Periodogram is identified as a shortcut method, easy to compute. It is limited in its ability to produce an accurate estimate of the power spectrum. Why? Because when it is applied on short data records, finite length data records, we have to confirm that periodogram converges to power spectrum. Let's see one after the other. So let's see the non-parametric methods of power spectrum estimation. These methods are based on the idea of estimating autocorrelation sequence of a random process. Autocorrelation sequence of a random process from a set of measured data. Then applying Fourier transform to obtain the estimate of power spectrum. Let us begin with periodogram. What is periodogram? It's a non-parametric method. It was first introduced by Custer in 1898 in the study of periodicities in sunspot numbers. Periodogram is easy to compute. It is limited in its ability to produce an accurate estimate of power spectrum, particularly for finite data records. So, periodogram of a Whiteson stationary random process is obtained from the Fourier transform of autocorrelation sequence. So, spectrum estimation, an autocorrelation estimation problem. Spectrum estimation problem is an autocorrelation estimation problem, right? So, for an autocorrelation ergodic process and an unlimited amount of data, autocorrelation sequence be determined by using time average. Time averaging. Limit n tends to infinity, 1 over 2n plus 1, summation x of n plus k into x asterisk of n. Autocorrelation ergodic process with an unlimited amount of data. The autocorrelation sequence in terms of theory may be determined using the time average calculation. If x of n is only measured over a finite interval, say for example n is equal to 0, 1, 2, 3, etc. n minus 1, then the autocorrelation sequence must be estimated with a finite sum. Now the formula is modified as summation n is equal to 0 to n is equal to capital N minus 1 x of n plus k into x asterisk of n. In order to ensure that the values of x of n that fall outside the interval 0 to n minus 1 are excluded from the sum. Now the same formula can be modified as 1 over n summation n is equal to 0 to n minus 1 minus k x of n plus k into x asterisk of n, where k is equal to 1, 2, 3, etc. capital N minus 1. Earlier it was shown as when the observation is available from n is equal to 0, 1, 2, 3, etc. n minus 1, we used a modified autocorrelation estimate as Rx of k. Now you can see that Rx of k cap is equal to 1 over n summation n is equal to 0 to n minus 1 minus k x of n plus k into x asterisk of n. Agreed? Because when you substitute n is equal to n minus 1, it will become n minus 1 plus k. So strictly to have values only in the interval of 0 to n minus 1, it's better to change the summation limit so that n varies from 0 to n minus 1 minus k x of n plus k into x asterisk of n plus x asterisk of n. The limits of k are also specified. Now let's see the values of Rx of k. For values of k less than 0, it is defined using conjugate symmetry property. Rx cap of minus k is equal to Rx asterisk of cap k, where Rx of k cap are all set equal to 0 for modulus of k greater than or equal to n. So applying the discrete time Fourier transform on Rx cap of k leads to an estimate of the power spectrum known as periodogram. Estimate of the power spectrum is called as periodogram by applying DTFT or discrete time Fourier transform on Rx of k cap. So let's see how to express the periodogram directly in terms of x of n. For example, we have n length sequence, finite length sequence of length n that is equal to x of n over the interval 0 to n minus 1. So xn of n is equal to x of n only over the interval 0 to n minus 1, and it is 0 everywhere. So xn of n could be treated as the product of x of n with a rectangular window. It's a windowed sequence, WR of n multiplied by x of n. So in terms of xn of n, the estimated autocorrelation sequence is now redefined as 1 over n xn of k convolved with x asterisk of n to the suffix n of minus k. It is called estimated autocorrelation sequence directly from the measured data given, measured data of the random process given to you. No extra work. Rx of k is obtained from 1 by n multiplied by the result of convolution of xn of k convolved with xn asterisk of minus k. Good. Now let us apply Fourier transform and use convolution theorem. Now we can see that the Fourier transform of Rx of k on the left hand side, Rxx of k cap is called periodogram estimate 1 by n multiplied by xn of e power j omega with xn asterisk of e power j omega, which can be comfortably written as 1 by n modulus of xn of e power j omega the whole square, where xn of e power j omega is equal to, as we mentioned that it is a discrete time Fourier transform of n point sequence. Discrete time Fourier transform of n point sequence. N point sequence xn of n e power minus j omega n, right? Usually it is a restricted length sequence, n is equal to 0 to n minus 1. So periodogram is proportional to the squared magnitude of DFT of the finite length record data, measured data, which gives you. So this is the practical flow. The finite length data is taken, record is taken, DFT is applied, the result is processed by absolute value estimator, modulus of x of n, xn of k, and then it is squared up, modulus of xn of k the whole squared, and it is scaled down by 1 by n. Finally, it produces the PPER, e power j omega, is actually PPER cap e power j omega, where omega is replaced by 2 pi k by en sampled. In this version, it is called DTFT. When you apply frequency sampling, it will become simply DFT result. Let us see how to interpret periodogram in terms of filter banks. Let Hi of n is an FIR filter whose impulse response is given by 1 over n e power j n omega I into WR of n. Actually, it is a sequence 1 over n e power j n omega I, which is windowed. So this will become 1 by n e power j omega I n for values of n is between 0 to n minus 1, and it is 0 otherwise. So if I find out the frequency domain representation using DTFT Fourier transform, I can find out that Hi of e power j omega is equal to summation n varies from 0 to n minus 1, Hi of n impulse response multiplied by e power minus j omega, and it is as per the DTFT formula. So the answer will be e power minus j omega minus omega I multiplied by n minus 1 divided by 2 into sine of n into omega minus omega I divided by 2 divided by n into sine of omega minus omega I divided by 2. So frequency response of the filter is known, impulse response of the filter is known. It is only one part of a filter bank. Let's see, one filter is alone taken, analyzed, and we have given you the results. So that looks like a band pass filter with center frequency is equal to omega I, and you can see that probably it's a narrow band filter with bandwidth is equal to del omega is equal to 2 pi pi n. So if a random process x of n is filtered with this filter Hi of n, the output process will be given by, the output will be obtained by. Band pass filter with the center frequency omega I is readily available when I apply this through a filter. Say for example x of n waits in stationary random process through a filter, it produces an output yi of n. That yi of n is returned as convolution of x of n with Hi of n. So the result is stated very clearly. Now let's see, yi of n can be obtained from, right, 1 over n summation k varies from n minus n plus 1 to small n. You can see that this is a finite length record, so x of k e power j n minus k into omega I. So yi of n, the equation is readily available. If I apply that through a filter, the filter is shown here, the filter is mentioned here. Now you can see that the magnitude response is equal to 1. So the power spectrum of x of n and y of n will be identical, equal, at a frequency omega is equal to omega I alone. So then the power spectrum of x of n and y of n are equal at frequency omega I, right? So Px of e power j omega I is equal to Py of e power j omega I. The bandwidth of the filter is very small enough so that the output power spectrum of x of n may be assumed to be approximately constant over the pass band of the filter. Thus, you can readily understand what is the power possessed in the output signal. Power in yi of n is equal to E of modulus of yi of n the whole square, which is equal to 1 by 2 pi integral minus pi to pi Px of e power j omega multiplied by, in general, input power spectrum multiplied by modulus of Hx of e power j omega the whole square. This is as per the rule Py of e power j omega, because you should know Py of e power j omega is equal to Px of e power j omega multiplied by Hx of e power j omega the whole square. This is the formula. So when you want to obtain the power possessed by yi of n in the output of the ith filter, then you can estimate expectation of modulus of yi of n the whole square is equal to 1 by 2 pi integral minus pi to pi Py of e power j omega multiplied by d omega. But it is to be replaced now. This is in the place of Py of e power j omega. As you know, Hx of e power j omega to omega I, it is equal to 1. So obviously this will simply become del omega by 2 pi Px of e power j omega I, or you can say that it is 1 over n Px of e power j omega I. Therefore, Px of e power j omega is equal to n times of the power possessed in the output sequence. Power in this term is called power in yi of n, right? So therefore we can give a conclusion how to obtain the output px of e power j omega. N multiplied by power n. N is the length of the finite length record. Thus, if we are able to estimate the power n yi of n, then the power spectrum of the frequency at the frequency yi of n can be estimated using this formula, isn't it? So px of e power j omega I, the power possessed in the input random process, estimate of the power possessed at the input of the random process, px of e power j omega I at omega is equal to omega I will be given by n multiplied by power in yi of n, power in yi of n. Right. One more approach, heuristic approach to estimate power using 1 point sample average. So let me say that the estimated or expected power possessed by yi of n will be equal to yi of n minus 1 modulus of yi of n minus 1 the whole square. 1 point average, 1 point sample average. What is yi of n minus 1? That can be easily understood from the formula. What is it? This is equivalent to say 1 by n squared, 1 by n squared, because I'll show you, because yi of n is known to you. yi of n is known to you. We know that yi of n is equal to 1 over n into summation k varies from n minus capital N plus 1 to small n, x of k into e power j n minus k into omega I. Before 2-3 slides we have seen that. Yes. Yes, yi of n, x of k into e power j n minus k into omega I. Now this is time for us to think about how to modify this according to small n is replaced by n minus 1. If you do that, it will become 1 over n squared summation k varies from 0 to n minus 1, x of k into e power minus j omega I k modulus the whole square. Now this is actually substituted into the power possessed at the input random process, which is equal to n times of modulus of yi of n minus 1 the whole square, isn't it? If it is to be replaced, if this part is replaced by the above formula, this n multiplied by 1 by n squared will become 1 by n. It is equivalent to periodogram. So this is taken as the derivation for periodogram equation. Periodogram can be viewed as an estimate of the power spectrum that is formed using a filter bank of filters which are actually band pass filters. You can see that in this video, x of n is applied through multiple banks of filters available. Bank of filters are available. E power j n omega 1, omega 2, e power j n omega n, etc. There are so many filters who each impulse response is given by, say for example, h1 of n or h2 of n. You can say, you can go up to, it is actually how many filters are L filter bank. So there are L filters, omega 1, omega 2, omega 3, omega L, and with respect to the input, when the input is applied, output is produced as y1 of n, y2 of n, y3 of n, yl of n. So output of normalization and magnitude, squaring up the magnitude process 1 by n into modulus of the input whole square will be equal to z1, z2, z3, zl. So you can find out that the power spectral density is computed as an output of bank of filters being derived from a single point average of the power in the filtering process. So the periodogram has such a filter bank built into it, so it is not necessary to implement the filter bank in fact, and filters are data dependent, and to have a frequency response that varies from with respect to central frequency omega I, it is quite evident to view that it is a narrow band pass filter. Periodogram may be viewed as the estimate of power spectrum that is formed using a filter bank of band pass filters was illustrated so far. Thank you.